Hello everyone, I hope you're doing well. In this video we are going to solve this problem. Okay, the solution to part A and C has already been uploaded and I will link the video in comment section. Okay, you can check it out. Now let's see what the part B says. An aluminium sample with FCC crystal structure is subjected to a uniaxial tensile load along 112 direction. Okay, the stress has been applied along 112 direction and the critical resolved shear stress is given by 50 megapascals. So tau CR, which is the critical resolved shear stress, it is 50 megapascal, and the direction of applied stress or force is 112. Okay, and in part 1 we are told to find out the initial slip systems. Okay, what are the most likely, most probable initial slip systems? It means when the force is applied, which slip systems are more likely to slip okay, to be active. So we'll find out those slip systems which will be active initially. Okay, so in part A we have to find out this, and in part B we have to find out the yield stress of the aluminium. So from the data that we will establish to solve the part 1, we will be able to find out the yield stress from the similar data. Okay, so let us start the problem. And we know that in order to know which slip systems will be active, we need to find out the critical normal stress. Okay, just as we did in our previous problem, we have to find out the critical normal stress, and the critical normal stress will help us to find out the most likely initial slip systems and also the yield stress. Okay, so we know that in aluminium we have 12 slip systems. Okay, slip systems represented by this family of plane. Okay, this is something that you have to remember. This represents the family of planes and this one represents the family of directions. So this is the thing, this is the basic thing about aluminium that you have to remember. Okay, and after that all of the data will be established based on this one thing. Okay, so yes, now we have this family of plane, and this is the family of directions. And let us first write the family of plane that it corresponds to, because there is no actually a particular slip plane that we are given with. Okay, we are taking all of the 12 slip systems and we'll see which is the most likely initial slip system. Okay, and for that purpose we'll see which slip system has the minimum critical normal stress. Okay, and that system which has the minimum critical normal stress will be the one which is most likely the initial slip system. All right, so yes, this is something that we are going to do. First of all, we'll have to write all of the possible planes in aluminium, slip planes, and these will be, the first one will have these Miller indices all positive. Okay, second one will be in which the first one is negative, in which the second one is negative, in which the third one is negative. All right, so these are the 4 possible planes, slip planes in aluminium. Now we are going to write the possible slip directions. Okay, and it will be first as 110. Okay, second is 1 bar 10. Okay, similar arrangement of indices is taken, but one as all positive and one as one of the index as negative. One of the index should be taken as negative, either this or this. Okay, but only one. And after that, one more permutation is possible, one more family equivalent equivalent direction is possible, in which we have another arrangement of 110 numbers. That could be 101. Okay, since all of these numbers were 1, that is why their position permutation was not possible, as it was equivalent writing 1 1 1. Since all of these numbers are 1 and changing the position of this one with this doesn't bring any change. But in case of 110, if we change this position with this, it will become this one plane. So we are going to write the family of planes, and it's 101, all of them positive, and then one of the index will be taken as negative, let's say the first one. And another arrangement is when we have 0 1 1, okay, and 0 1 bar 1. Okay, these are the possible slip directions, and these are the slip planes, and these are all possible slip directions. I hope you understood how I wrote the slip directions. So in that way we can write the slip direction. Now we need to find out which plane has which slip direction, and because there are the 4 different planes, and not all of the planes have all of these slip directions. For example, this plane will have any for example 2 to 3 slip directions from these 6 slip direction. Not all these directions will be its slip direction. We have to determine slip direction to a particular plane separately, for this plane separately, for this plane separately, and for this plane separately. And in order to find out the slip direction to a given slip plane, what we have to do is to take the dot product between the slip all of the slip directions with the corresponding vector of the normal vector of the plane. Okay, and the combination which has the dot product equals to 0 will be the slip system. Okay, they will comprise a slip system. Slip system means a plane and a corresponding slip direction. Okay, so in order to find out that slip system, what you have to do is to take the dot product of the normal vector to a plane, okay, for example of this plane, with each of these slip directions. Those which have the dot product equal to 0 will be the slip systems, and those which do not have any which have non-zero dot product will not be the slip system. They will not form the slip system. Okay, so this is the calculation that we have to do in order to find out the slip systems. Okay, so let us do this first for slip plane 111. Okay, we have to find out the slip system. So now we are going to write the dot products. Okay, and I'm using the coordinate terms. First dot product with this one. Okay, you can do it in column, then dot product with the second slip direction. Okay, and then dot product with third one, then with fourth, fifth, sixth. Okay, so let us do it for this one plane. 1 into 1 plus 1 into 1 plus 1 into 0 gives 0, so it is 2, which is non-zero, hence this will not form a slip system. Okay, this combination will not form a slip system. Now for this one, 1 into minus 1 is minus 1, 1 into 1 is plus 1, plus 1 into 0 is 0, so minus 1 plus 1 gives you the 0 result. So this this combination will form a slip system. Okay, 111 plane 1 bar 1 0 direction will form a slip system. So we have a slip system 1. We'll write it at the end. Okay, we'll do this similar thing for all of the directions. Okay, we have to do this, and this will result into a non-zero digit. Okay, 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is again 1, it gives 2. So this is not a slip system. This one will form a slip system. Okay, you can check it. This will not form a slip system, this will form a slip system. So we have got 3 slip system for the plane 111. Okay, so slip system 1 is 111 plane, and the direction was minus 110, which is 1 bar 10. Okay, slip system 2 is equals to 111 plane and 1 bar 01 direction. Similarly, slip system 3 is 1 1 1 1 0 1 bar 1 direction. Okay, so we have got 3 slip system. Now we'll do it for this plane, then for this plane, and this for this plane. The similar procedure will be done, and we will find out the dot product of each plane with all of these directions. Those combinations which have dot product equal to 0 will form a slip system. Okay, and we have to do it for all of the planes. I'm not doing it for all of the planes. I'll do it for one more plane, and then I will move further. I will write the result, that is the final slip systems, directly. You have to derive it on your own because I have shown you the method, and you can do it now on your own. Here are the final slip systems. Okay, you can count them: 3 3 3 3 3 into 4 is 12. They are the 12 slip systems in aluminium, and all of these are the slip systems. Okay, so these are the final slip system that you will get following this method. Okay, you have to follow this method and you will get these all slip systems. I can't do it for all of them, it will become too much lengthy. The process is easy, and as I have shown you for one of the plane. Okay, now you can do it on your own. Now we know all of the slip directions. Okay, we'll proceed with, we know that we know that the critical normal stress is given by sigma y equals tau CR by m, where m is the Schmidt factor. Okay, something like that. Okay, m is the Schmidt factor, and it is cos of phi into cos of theta. Now cos phi is constant for a given slip plane and applied force. Okay, it will be different for different planes, and cos theta is different for all of these different slip directions. Okay, we have to calculate them separately, and we will put the value into this formula to get the value of critical normal stress, and that critical normal stress chart will give us the data we need to find out the answer to the question we are solving. Okay, so sigma that tau CR is already given, which is 50 megapascal. Okay, but cos phi and cos theta needs to be determined. So let us now find the value of cos phi for the 4 of the planes that we have selected. Okay, so for plane 111, okay, cos phi is given by the dot product of plane and dot product of the direction of force, which is 112, and the vector normal to the plane. The vector which is normal to the plane is actually 111. Okay, as we already know that a vector that is normal to the plane with Miller indices HKL will be the vector with Miller indices HKL. Okay, so cos phi, let us call it as cos phi 1, okay, for this plane, and it will be equals to 1 1 2. Okay, I'm writing it in coordinates form, and dot product with the direction of the plane, and here it is divided by the their magnitudes. Okay, magnitude of this vector into magnitude of this vector. So 1 square plus 1 square plus 2 square, which is 4. Okay, magnitude of a vector is given by taking the square of this quantity plus taking the square of this quantity plus taking the square of this quantity and whole under root. Similar procedure will be done here, and 1 into 1 is 1. Okay, we are taking the dot product, so 1 into 1 is 1, plus sign, 1 into 1 is 1 again, 2 into 1 is 2, divided by under root 6 into under root 3. So it's 2 plus 1 plus 4 by under root 6 into under root 3. Okay, this is cos phi 1. And if you want to simplify it further, then it's up to you. I'm leaving it like as it is. Okay, now for plane 1 bar 1 1. Okay, we are going to find out cos phi 2, and for this we'll take the dot product with the force and with the vector, and it will give us 1 into minus 1 is minus 1 plus 2 divided by under root 6 into under root 3, so that it becomes 2 by under root 6 under root 3. Okay, this is cos phi 2. Similarly, we will do it for 1 1 bar 1. Okay, cos phi 3 1 1 2 dot product with 1 minus 1 and 1 divided by under root of 1 square plus 1 square plus 2 square dot under root of 1 square minus 1 square is again 1. That is why we are taking it as 1 again. So 1 into 1 is 1, 1 into minus 1 is minus 1, 2 into 1 is 2. So it is like that. And okay, now for plane 1 1 1 bar. Okay, cos of 4 is equals to so it is 0 here. Here cos phi 4 is equals to 0, so it means we can see here that if we put cos phi into this expression, there is 0 in the denominator, so the quantity becomes infinite. Okay, so it's optional if you want to put it here and write it as infinity. Okay, it's optional, but we don't need it. Okay, so we'll neglect this one plane further on, and the rest of the calculation will be done for these three planes. Okay, we'll consider these three system. Okay, these three slip systems, and this slip system will be neglected further on for the reason that the cos phi is 0 for them, and it is not like worth it to proceed with this slip system. All right, so we are not considering the slip system that contains the plane 1 1 1 that one 1 1 1 bar. Okay, we are not considering it. Now we'll take these slip systems only. Okay, now let us calculate cos of theta for each of these 9 plane system slip systems. Okay, so we have 9 slip systems left, and we are going to calculate the value of cos theta for them. Now cos theta is obtained by taking the dot product of the direction of the force and the slip directions. Force direction, which is 1 1 2, with slip directions. Okay, so cos of theta 1, first of all we'll do the slip system with plane 1 1 1. Okay, and its slip directions. So cos theta 1 will be equals to, for slip system 1, the force, which is 1 1 2. Okay, its coordinate multiplied by minus 1 1 and 0, minus 1 1 0, divided by their magnitude. 1 into minus 1 plus 1 into 1 is 1, 2 into 0 is 0. So it is 0. All right, now for slip system 2, cos theta 2, that is equals to 1 into minus 1 is minus 1, 1 into 0 is 0, plus 2 into 1 is 2. So it is under 6 into under 2, minus 1 into plus 1 is plus 1 divided by under root 6 into under root 2. Okay, this is cos theta 2 equal to 1 over under root 6 into 2 is 12. Okay, this is cos theta 2, which came out to be non-zero for the slip system 2. Now cos theta 3, you should remember which slip system has which cos of theta. Okay, and now for this slip direction, 1 into 0 is 0, plus 1 into minus 1 is minus 1, plus 2 into 1 is 2. So it becomes 1 over under root 12. This is cos theta 3. Alright. Now for slip system 4, 0, 1, 1. 0, 1, 1. So it's 1 into 0 is 0, 1 into 1 is 1, plus 2 into 1. This is cos theta 4. Now cos theta 5. 5 is minus 1, 0 and 1. Minus 1, plus 2. This is cos theta 5. Now cos theta 6. Now cos theta 7. Now cos theta 8. This is 2 over under root 12. Okay, this is cos theta 8. And last one is cos theta 9. Denominator of every case is similar, so that is why I am writing it directly. So now we have got the values of theta and also phi. So now we can find the value of critical stress, critical normal stress for different slip systems. Okay, so let us do this now. For slip system 1, okay, and it is so we'll put 50 megapascal here divided by cos phi 1, and cos phi 1 was 4 by under root 6 into under root 3. Okay, this was cos phi 1 for the plane 1, 1, 1. That will be multiplied by cos theta 1, and cos theta 1 is 0. Okay, so the result become infinite because there is 0 in the denominator, so that we also write as undefined. Now sigma 2, which is slip system 2. Now slip system 2 has the similar plane 1 1 1, so cos phi 1 will be used. Okay, because phi depends upon the plane. Since the plane is same, so cos phi 1 will be used with cos theta 2, and it's 50 megapascal divided by cos phi 1, which is 4 by under root 6 into under root 3, and cos theta 2 was 1 over under root 12. Okay, so these things goes up. Let us calculate it and write its result. Here it is 183. Okay, megapascal. There are 9 slip systems, so we'll get 9 values now. This one, the third slip system is again for 111 plane, that is why phi cos phi 1 will be used with cos theta 3 in it. So 50 megapascal cos phi 1, which is 4 by under root 6 into under root 3 multiplied by cos theta 3. Cos theta 3 was 1 over under root 12. It will result the similar thing because it was same in that case of sigma 2. So we'll get 183 megapascal again. Now sigma 4. Sigma 4 corresponds to a slip system with plane 1 bar 1 bar 1. So cos phi 2 will be used and cos theta 4 will be used. Okay, these subscripts will be same, while this subscript depend upon the plane we are considering. So it is 50 megapascal divided by cos phi 2. Now cos phi 2 is 2 by under root 6 in under root 3, while cos theta 4 is 3 by under root 12. Let us calculate it. So result is 122. Okay, sigma 4 corresponds to the second plane. Okay, and the slip system number 4. Okay, we have already written their names here as the slip system. So this slip system has the normal critical normal stress as 122 megapascal. Okay, just remember that. Now we need to calculate sigma 5, which is sigma CR by cos phi 2 again, because the plane is same. Putting the values, cos phi 2 is 2 by under root 6 into under root 3, cos theta 5 1 by under root 12. Okay, so it has 367 megapascal. Okay, sigma 5. Now sigma 6 cos phi 2 again multiply by cos theta 6. Cos theta 6 is 2 by under root 12. Okay, and the result is 183.7 megapascal for sigma 6. Now sigma 7, sigma 8 and sigma 9, which will correspond to the third plane. Cos phi 3 and cos theta 7. Okay, cos phi 3. Here is cos phi 3, 2 by under root 6 under root 3. Cos theta 7. Here is cos theta 7, 3 by under root 12. Okay, so this is something that we have got before. Yes, this one, which resulted into 122 megapascal. Sigma 8 and sigma 9, you can calculate it yourself, and both of these values will let us do it. Cos phi 3, which will be this, into cos theta 8. Cos theta 8 is 2 by under root 12. Okay, and the result will be 183.7 megapascal. Okay, and similarly for sigma 9, 50 megapascal divided by 2 by under root 6 into under root 3 multiplied by cos theta 9, which is 1 over under root 12, and it will give us 367 megapascal. Yes, so now we have got all of these values of critical normal stress, and we can see here the slip systems which have the minimum critical normal stress. Okay, slip systems which have the minimum critical normal stress will be probably the slip systems which will go initial slips. Okay, so now we can see here the minimum value that we got for the critical stress is, it's not 183 megapascal. Okay, infinite is very large value, so it's not included. 183, 122 for sigma 4, and 122 again. We got 122 two times, and all of the other values are greater than 122 megapascal. This 122 megapascal is the least value that we got for the critical normal stress, and hence sigma 4 and sigma 7 corresponds to a slip system that will go initial deformation. Okay, initially they will show deformation for the first time. Okay, and the other slip systems will be active later. Okay, first they will be active, so these are the initial slip systems, and hence most likely initial slip systems are, then we have to write the slip system 4. What was the slip system 4? Okay, we have to write it down. Slip system 4 is this one. Okay, and slip system 7, which is this one. Okay, this and this one, these are two the initial active slip systems. This plane with direction, and this plane 1 bar 1 1 and direction 101 are initial slip systems, more likely to be initial slip systems. Okay, and in part B we are also told to find out the yield stress of aluminium, and yield stress is the minimum stress needed to produce produce plastic deformation, okay, which is 122 megapascal. We have seen here that 122 megapascal is the least critical normal stress that is needed to produce plastic deformation, and hence the yield stress of aluminium will be 122 megapascal. Okay, and that is the answer to this part of the question. I hope you got it.